All right, three, two, one, let's go. All right, welcome to the pre-recorded video for the 18th. University went remote today, so I'm not feeling too hot. I can hear my voice sounds a little weird, but anyway, all right. Plan for today: we are going to continue the conversation on orthogonality, and after that, we'll then get into the Gram-Schmidt process. Good stuff. Okay. All right, last time we finished talking about dot products and inner products in CN. And we're going to generally stick again with Rn for things, but everything for Rn can be upgraded to CN, where instead of using the dot product, as we see here, you would use the inner product instead. Okay. All right, so recall that we announced a list of things in Rn to be orthogonal if their pairwise dot products are equal to 0. And again, a distinct pairwise products. Obviously, if we didn't include this, that would mean vk dot with vk is equal to 0, but we know that that would then force vk to be 0, the 0 vector, and so the only things that could be orthogonal would be 0 vectors, which we're not particularly interested in. Yeah. Okay, so we introduced this, and we noted that this is sort of the right definition for it if we look at how the law of cosines behaves in R2. And comparing the law of cosines with some of the dot product and norm properties we had established. All right. Okay, and last time when we introduced orthogonality, we just immediately jumped into a proof. But before we do that, again, let's look at some examples. Okay. So, look at that wonderful spelling right there. Orthogonal. All right. So, first, note by the definition that to be orthogonal, you need that for any distinct pair, the dot product is 0. Note that that would ensure that any single element would count as orthogonal because, right, there's no distinct pairs to require, right? So, again, this is an if-then statement. So, if this, then that needs to occur. Well, if the hypothesis is never satisfied, the implication is always true. From any false assumption, you can conclude whatever you want. Right, so this, again, is that example of a vacuous truth. Right, and again, you want to keep in mind those sorts of things whenever you cook up a definition. It's possible that you've got something that maybe you didn't exactly intend to be true, but it's true. All right, now let's look at a pair of elements. Here I have v1 and v2, and note the dot product equals 0, so hey, these are orthogonal. However, x1 and x2 here now, after a slight modification, this no longer counts as orthogonal, as the dot product is not equal to 0. But it is worth noting here that both of these are linearly independent sets. Right? It's hopefully pretty easy to see that. Good luck scaling this and creating this. And likewise from here to here. All right, let's go over to a set of 3 elements. All right, so these 3 fail to be orthogonal, even though the dot product of the first and the second is 0. And the dot product of the second and the third is also equal to 0, so it's really close to being orthogonal. But the first and third element failed to have a dot product of 0. Right, even though you've got a lot of zeros, there's one that fails. One of the possible distinct pairs does not dot product to 0, so tough. Not orthogonal. Okay. All right. So note that it is possible, though, that you do have orthogonal subsets hanging out, right? So, for example, x1 and x2 themselves are orthogonal, x2 and x3 themselves are orthogonal, but all 3 of them together fail to be. But again, though, note something I pointed out here, linear independence. It takes maybe a little bit of effort to see it, but it's true that x1, x2, and x3 are linearly independent. Smush these 3 vectors together, compute their ref. The ref will be the identity matrix, so null space is trivial, definitely linearly independent. That's kind of interesting that we're seeing linear independence flying around here. And I wonder if there's some connection between orthogonality and linear independence. And as we saw in R2, linear independence can happen if your vectors are pointing in different directions. Well, if you're orthogonal, they're pointing in, like, literally the most opposite direction they kind of can be. Meaningfully, obviously, if you go 180, it's total opposite, but then you're on the same line. Okay. So, seems like there might be some connection between orthogonality and linear independence. And I wonder if that's like the content of the big thing for today. Okay. Alright, so first off, before we get to that, let's recall that the thing for orthogonality that we proved last time was a super version of the classic Pythagorean theorem. If you have a right triangle, then a squared plus b squared equals c squared. We noted that, we now have a list of things that can be all pairwise perpendicular to each other, and since we also can throw in some scalars, we would like to know, hey, if I form this thing and look at the length squared, do we get the sum of the length squared, right? Do we get a squared plus b squared equals c squared? The answer is yeah, you do. So we kind of have this super version of the Pythagorean theorem at our disposal, and equipped with this, we're not going to peel back the curtain. Indeed, orthogonality will ensure linear independence. Hey, that's kind of nice. However, we do need to require that the vectors themselves are non-zero, and we'll see exactly where in the proof you need this. That's a good just general math principle to keep in mind. If you have a hypothesis, and then you do a proof, and at no point did you use the hypothesis, did you actually need it? Okay. Alright, so want to prove something is linearly independent? Well, let's go directly from the definition, scale, and add them up and set it equal to 0. We need to prove that all the scalars are 0. Okay. Alright, well, if you look at the norm squared, since this is equal to 0, its norm is 0, but since everything involved is perpendicular, this breaks down like that by the Pythagorean theorem, and now my hypothesis was that all of my vectors are non-zero. That means all of these norms are non-zero. So the only way this summation can hit 0 then is if all of the scalars were 0 in the first place. All of these are strictly positive numbers, so the only way this could hit 0 is if all of these were actually 0 themselves. And there we go. Cool. So that actually reveals something interesting. This tells us that if you have a linearly dependent set, it can never be orthogonal. That's kind of nice. Right. But now with this is kind of the natural reverse to ask, right? We've already seen examples where you're linearly independent. Man, there's some good spelling on the document today. But orthogonality is just not possible. It's easy to cook up examples of this. But then naturally you would like to go, okay, well, let's say I had something linearly independent. Can I make it orthogonal? Right, so in R2 you can imagine in your mind's eye you got two vectors, they're linearly independent, so they're not pointing in the same direction. And then you can take one and kind of crank it until you get a 90-degree angle. And don't put like too much to convince yourself that you're going to be able to do that for any size of vectors in any situation. And that's the content of the Gram-Schmidt process. If you have a list of linearly independent things, then you can find, ignore that. I rewrote it as that. So, go and pretend that's not there. Anyway, given a list of linearly independent things, we can concoct orthogonal things that have the same span. So you can take your linearly independent set and pull the vectors apart until you've got 90-degree angles between all of them, and it's not going to screw up the spanning set that it creates. Cool. Okay, now, right now, of course, this is something we can prove in the next lecture, which will be on Friday, which again will be another pre-recorded one. We'll talk a little bit about kind of why you would want to do this. So right now we're a little more preoccupied in can we do it? The should we do it? We'll get to that next time. All right, so this is gonna be the big proof for today, and this is gonna be our first real heavy proof. There's gonna be a lot of heavy lifting here. This is probably gonna be this is up until now gonna be the most challenging proof we're gonna do. So buckle up, buckaroos. Okay, so the way we're gonna attack this is by induction. Alright, and it's pretty easy to see the base case, because you just let V1 be X1. A single element has to be orthogonal, as we pointed out. X1 comes out of a linearly independent set, so it has to be non-zero. And obviously the spans are the same, because it's the same damn thing. Alright, so then for the induction hypothesis, suppose that I have actually constructed a orthogonal list of non-zero things with the same span as the x's. So I just need to tell you how to find VP plus 1. I just need to tell you how do we make the next thing that keeps the orthogonality, keeps non-zero, and keeps the spans coinciding. And here it is. That's the computation. Yep. Now, again, at first glance, there's a lot going on here. There's a lot of like, okay, why is any of this being computed? But if you ignore all of this highlighted stuff here for a moment and just look at that, if you've taken Calc 3 before, this looks a little familiar. This looks maybe super familiar. Like it's a projection. Ooh. And we'll talk about projections when we talk about linear transforms. So right now, the word projection doesn't really mean much to us. But if you let your mind float back to a previous math class, you might recognize this quantity right here. All right. Okay, I claim that this is the thing we need, so we need to prove that it's non-zero, we need to prove that it's perpendicular to all of the previous elements, and then we need to prove the spans line up. Alright, and the non-zero is basically immediate, because if this is zero, then these two things need to equal each other. But where does this live? This lives in the span of V1 to VP, because it's just a linear combination of V1 to VP. But V1 to VP has the same span as X1 to XP. That was part of our induction hypothesis. Alright, but what's part of our actual hypothesis? That these things are linearly independent. Well, if XP1 is a linear combo of the previous elements, then the full list can't be linearly independent, because this is some linear combo of these, and then everything after P1 you could just zero out using scalars, and then you could create a linear combo that's equal to 0 with non-zero scalars, so there you go, linear independence is out. So what I'm working with here has to be non-zero. Okay. And again, note, we need that because we're trying to take this linearly independent set and create an orthogonal set with the same span, but we want orthogonality to ensure also linear independence, and that's where you need the non-zero part of the vector. Okay. Alright, so now we need to demonstrate that VP plus 1 is perpendicular to all of these. All of these are mutually perpendicular to each other, so I don't need to worry about their dot products. I just need to take VP plus 1's dot product with one of these. So let's call that X sub j. Alright, and write out what you have. You've got Vj dotted with this, and that's equal to that. And then now we just remember how dot products work. I can distribute this dot product across. I can pull out scalars and break out sums across a dot product. Alright, and then in here, what's going on? Well, the V1 and the VP are all orthogonal to each other, so all but one of these terms is going to drop out, specifically the Vj term. And then now we kind of see why you needed to divide out these dot products here. Again, also, that's another reason for the non-zero-ness. We need these dot products to be non-zero in order to divide by them. Right, and so those cancel, and here we see, hey, dot products are nice and symmetric, so that difference zeroes out. Proof's over. No, the proof's not over. That part of the proof's over. So now we have that VP plus 1 is non-zero. We have the orthogonality. Now we just need to show that the spans will coincide. And all we need to do is show that when I add VP plus 1, I pick up XP plus 1. And when I look at the span from X1 to XP plus 1, I also pick up VP plus 1. Right, because these two spans from 1 to P are equal to each other, to show that if I add P plus 1, I just need to show that only the extra element lands in the opposite set. Then you get a linear, then the spans will have to coincide with each other. And this is immediate from the construction, right? VP plus 1, we already noted, is equal to this linear combo, and that lives in the span of V1 to VP plus 1, because again, it's a linear combo of those elements. So VP plus 1 is the only one we need to verify now, but that one's easy to see because this linear combo lands in the span of X1 to XP. So this is some linear combo of X1 to XP, and then when we throw this part in, well, then it belongs to that span. And that completes the proof. Alright, there you go. Gram-Schmidt process. We got it. Okay. And like I said, this is the proof of an incredible amount of heavy lifting. Right. It's an induction argument, which, again, we've seen those, not too bad, but this is a pretty hefty induction. And it's relying on a lot of previous ideas that we've established, right? This idea of a spanning set, these ideas of linear independence, all of these properties of dot products. I mean, this really is kind of our first, like, really big, hefty proof. Now, the good news about the Gram-Schmidt process is that it's an existence proof. It says there exists orthogonal things with certain properties. But note, our proof actually told us how to construct it. So there's two kinds of existence proofs in mathematics. There are the ones where you prove something exists, but I don't tell you how to find it. I just tell you that you can find it. Right? It's out there. It has to be. If it doesn't be, we got a problem. The other kind of existence proof is I explicitly tell you how to create it. And in this, we actually get this sort of a recursive definition, right? Note that it was an inductive proof, and as we noted, there's this connection between recursion and induction. Right, so I told you how to make the first element, and then I told you how to make all the elements after that. So let's finish up today with an explicit example of this. Calculation. Okay. So, the Gram-Schmidt process is a great proof because it tells us how to perform it. Right, here's a list of 3 elements in R3, very similar to the one we saw before, and it doesn't take too much effort to show that this is clearly not orthogonal. x1, x2, dot product to 1, so not orthogonal. It's easy to check that it's linearly independent. Again, combine the 3 vectors into a matrix, compute the ref, you'll get the identity matrix. Alright, so let's actually go through computing the associated orthogonal set with the same span. Alright, well v1 is x1, so we don't have to do anything there. v2 has to be x2 minus x2 dotted with v1 all over v1 dotted with v1, scaling v1. And I've done the computation for you. Right? Note that it just eliminates that top element so that now x1 and x2 are perpendicular to each other. Alright, now for the hefty computation, v3 has to be x3, then minus 2 things, right? Because again, in the construction that we see up here, right, there's a summation. So note, if you have to do Gram-Schmidt on like 12 elements, you're gonna do a lot of computations. Don't worry, 3 is the most I'll ever force you to do. There might be elements of R4, but 3 is the most I'll ever make you do. Alright, and here we see, you just run through the computations. And note, again, it's very easy to screw up this computation. There are minus signs running around. You got to be careful of these x3s are constant across the board, but the v's are changing at each step. Okay, and we compute it, and we get 0, 1, negative 1. Great. Hey, Gram-Schmidt, we did it. We proved it. We saw an example. Life's good. All right. Okay, so next class will be problem session, and then Friday we'll have another pre-recorded lecture where we'll explore kind of the why. We've shown the yes, you can do this. You can take a linearly independent set and create an orthogonal one with the same span, but we kind of want to address, well, why would anybody care about doing this? Right? And we'll see why. And spoilers, the answer is something called least squares, which maybe you've heard of. All right, cool. All right, that's it for today. See you next time.